Welcome back. What we're going to do in the second half of this course session is to continue our exploration of vector geometry. We left off by looking at how to write equations for lines in the plane. What we're going to do now is to examine an important operation over vectors, which is called the dot product. In fact, this is an operation that you already know and use all the time when you are multiplying matrices. In fact, multiplying two matrices is nothing but repeatedly applying the dot product operation over two vectors. If you have two vectors, v and w, of the same length, the result of taking the dot product of the two vectors is a number, just like when you multiply the row of a matrix with the column of another matrix, what you get is an entry, that is to say a number, in the matrix that results by multiplying the two matrices that you're multiplying. So what is this number? Well, it's the number that you obtain by summing together the numbers that you obtain by multiplying similarly positioned entries in the two vectors. So you multiply the first entry in V with the first entry in W, second in V with the second in W, nth entry in V with the nth entry in W. And you sum them all together. So this works in any dimension n, but in our examples, we will focus on R2 and R3. Even though in most computer science applications, you actually want to do the dot product of very long vectors. Thousands and sometimes hundreds of thousands, sometimes millions of entries. Now, before we look at possible applications of the dot product, let's look at some of the properties that this operation has. Well, first of all, the dot product is commutative. It doesn't really matter whether you take the dot product of V and W or W and V. The result is the same. Why? Well, because multiplication of numbers is commutative. It doesn't really matter in what order you multiply things. And also addition is commutative anyway. Not that it makes that much of a difference here. If you multiply a vector by the zero vector, you take the dot product, sorry, of a vector and the zero vector, you're going to get the number 0. Well, why? Because you're multiplying, say, v is 0, is the zero vector, then x1 is 0, x2 is 0, and if you multiply something by 0, you get 0. And if you add 0 many times to itself, you get 0. If somebody gives me 0 kroner many, many times, well, I'm not rich. I still have nothing. So far, so good. But this begs a question that I'm going to ask you right now. So this says, if I multiply v with the 0 vector, I get 0. But suppose now I tell you I multiply v with another vector w, and I get 0 out. Does it mean that one of the two vectors is 0? One of your colleagues immediately said no. So let's see. What I asked for, okay, suppose I tell you I take two vectors, u and v, and I take the dot product, and the result is the number 0. Does this mean, does u equals 0 or v equals 0? And one of your colleagues is saying no. Goodness says no, not computer says no, in this case. And he's right. Can you give me an example of two vectors which are not 0, but their dot product is 0? Okay, let's take 1, 0. and 0, 1. Their dot product is 1 times 0 plus 0 times 1, which is equal to 0 plus 0, which is 0. We will see in a few minutes that the fact that the dot product of these two vectors is 0 tells us something geometric about these two vectors. Well, in fact, I think you can already tell that there is a special relationship between the vector 1, 0, which is this one, and the vector 0, 1, which is this one. So this is 0, 1, and this is 1, 0. What is this special relationship? Okay, let's consider this vector 1, 1. And let's consider, say, this vector here. That's the vector 1, minus 1. What is the dot product of 1, 1 dot product with 1 minus 1? It's 0, 2, because it's 1 times 1, which is 1, plus 1 minus times minus 1, which is minus 1. So 1 minus 1 is 0. Hey. Well, let's look at this angle. That's 90 degrees. Let's look at this angle. That's also 90 degrees. In fact, these are perpendicular or orthogonal vectors. So if you take two vectors that span an angle of 90 degrees, they are perpendicular to one another. When you take their dot product, it's always going to be 0. In fact, two vectors are orthogonal. They form an angle, they are at an angle of 90 degrees one with the other, if and only if their dot product is 0. Okay, so if somebody asks you, okay, here are two vectors, are they orthogonal? Well, you compute the dot product. If the answer is 0, then yes, they are. If the answer is not 0, they are not. Okay, so what is it that we've learned? We've learned that two vectors which are not 0 can have a dot product equal to 0. And this happens exactly when these two vectors are perpendicular one from the other. So in fact, without drawing anything, well, without actually giving you anything but a drawing, so if I draw this vector and this vector here, and I ask you, can their dot product be 0? Your answer would be no, because this angle that I have here, that's not 90 degrees. It's smaller. Or, well, actually, it's different from 90 degrees. Okay, you don't need to calculate the dot product. In fact, there is a general formula that involves cosines that I'm not going to give you in this course that will tell you how to calculate the dot product of any two vectors based on the angle that they span. Excellent. Okay, what else? So if I take the dot product of a vector with itself, what I get is the square of the length of the vector. Why is that? Well, let's look at the formula here. Well, actually, let's calculate. So if I give you a vector, let's, for simplicity, just take a vector AB. So that's my vector in 2 dimensions. What is the formula for the length of this vector? Well, we don't need to remember that, do we? So that's the vector, that's AB. What does this mean? This means that this is A, and this thing here is B. So the length of the vector is this thing here, the length of this side of a triangle, of a square triangle. How do we calculate it? By using a theorem that is due to Pythagoras. And what does Pythagoras' theorem say? Well, that this is the square root of a square plus b square. Is that okay? Does everybody agree with that? Now, how is this related to the dot product? Well, if I take the dot product of V with itself, what is this? Well, that's A times A plus B times B, which is nothing but A squared plus B squared, which is what? Well, it's actually the square, it's the square of the length of the vector D, of the vector V, sorry. Because the length of the vector V is nothing but the square root of A squared plus B squared. So you can use the dot product to calculate the length of a vector, provided you take the square vector, the dot product of the vector by itself, and then you take the square root of that. Okay? If I'm abusing of your intelligence, scream, or throw some food at me because I'm going to eat it. Okay, so here are two more properties of the dot product that tell us how the dot product interact with scalar multiplication and with summation of vectors. Suppose that you want to take the dot product of K times V and W. Well, that's K times the dot product of V and W. I encourage you to try and convince you that that's the case. It's just a matter of using this formula. Moreover, if I take the dot product of U with the vector, which is the sum of V and W, well, you can distribute. So this is actually the sum of the dot product of U with V and of U with W. And again, it's just a matter of calculating with the formula that you have here. But it's not that I'm ever going to ask you to do this proof, but it could be a good idea to remember or to note down on your cheat sheets for the exam, which is going to be held on April 13th. It's not a Friday, so you should not worry too much about that. It's a Tuesday, I believe, but I may be wrong. Anyway, it's not a Friday. Okay, now you might say, okay, the dot product, we already use it when we multiply matrices. What are the uses of the dot product in real life? Because in real life, we don't often multiply matrices. So that's what you think. In fact, we do all the time, at least in computer science. So here's an example of how you actually use the dot product every day when you go shopping. Okay, suppose you go to Netto, and you have a shopping list for your favorite recipe. Here, the vector V describes the amount of all of the ingredients that you need to bake your favorite cake, God forbid. X1, X2, Xn. These are all the ingredients and the amount for each ingredient. Now, stuff costs. I mean, nobody gives you anything for free. So here's a vector W that tells you the unit cost for each one of the ingredients that you need. So Y1 is the unit cost for the first ingredient, of which you need X1 units. So for instance, if the first ingredient is an egg, you need X1 eggs to bake your cake, and one egg costs Y1 krona. Well, what is the dot product of V and W? It's the total cost of your shopping list for baking the cake. Why? Because it's X1 times Y1 that tells you how much the eggs are going to cost. If X2, it tells you how much flour you need, and Y2 tells you what is the unit cost for flour, then X1 times Y2, X2 times Y2 tells you how much you're going to spend on flour. And you sum them together, and you figure out how much you're going to spend overall. So every time you're actually going shopping, you're doing dot product computation. Well, actually, the cashier is doing dot product computation for you. Or actually, the machine helping the cashier figure out how much you need to pay is going to do that for you. It's the machine, because every time you actually change something, the cashier goes into pain, into trouble. Because she doesn't, or he doesn't know how much change you need. Fantastic. Now let's take another real-life application. This time, this has got nothing to do with shopping. It's got everything to do with politics. Okay, so we are in the Icelandic parliament, say, or the Italian parliament for what matters. If we were in the Italian parliament, you would be fighting with one another, punching each other in the face. Probably this doesn't happen in the Icelandic parliament, but it does in the Italian parliament every now and then. So let's make it the Italian parliament. It's much more fun. Unless you're the one being punched, that is. Okay, so suppose you want to figure out whether MP Berlusconi and MP Grillo agree when they vote for parliament bills. Okay, somebody has a new law. You want to figure out if they actually share the same opinions. And you want to do this, since you're a linear algebra guy and a computer scientist, you want to do this using dot product. You know what? You can. So all you need is a vector that tells you, that gives you relevant information about how Berlusconi voted for each one of the bills. So for the first law, we put a -1 because Berlusconi voted against. For the second one, we put a 1 that tells us that Berlusconi voted in favor. And you use a 0 to mark when Berlusconi abstained. He didn't vote. You can also use this to mark his preferences regarding girls, especially if they are underage, but that's another matter. Okay, now I'll stop talking about Berlusconi, because otherwise he's going to chase me even on YouTube, but that's another matter. Okay. So suppose you have the same information stored in a vector regarding my votes. And now you want to, assuming I'm an MP, which I'm not. And now you want to figure out whether I agree with Berlusconi. Can you do this using a dot product computation? So suppose Berlusconi and I agree a lot. What would the result of the dot product be? One of your colleagues is saying close to 1. But okay, every time Berlusconi and I agree, it means that we are either both in favor or against. Which means that this is going to contribute a +1 to the dot product computation. So the more we agree, the more +1s we are going to have. So if we agree a lot, we agree most of the time, the dot product is going to be positive, possibly highly positive. If instead we disagree all the time, we are going to get lots of -1s. Which means that the dot product is going to be on the negative side. If instead, well, we agree to disagree, we disagree most of the time, we are going to get close to 0. Somewhere in the middle. Okay, so you can actually use dot product computation to see when different people agree on their tastes. In this case, the example is for the parliament, but it could be anything. It could be on whether they like a product. People like you who bought this book, they also bought this other one. Have you ever seen anything like that? It looks like Amazon does a lot of it, for one. And you can calculate similarity in tastes using dot product. Here's something closer to you. Okay, well, I'm sure you log into websites quite a bit. At least I do. And very often I ask my browser to remember the password for a website because I cannot be bothered to remember all of the passwords that I use all over the place. Now, that's a little bit leaky, if you wish. Somebody just gets hold of a password and it can pretend to be you. Well, here's a different scheme for logging in to your favorite website. Okay, of course you have a password, which the website knows about. But the website doesn't just ask you type your password, and if you get it right, you're in. The website starts a challenge response protocol for logging in. It sends you a question about the password. You reply. The computer then asks you another question about the password. You reply. And the question typically is not what is your password? Otherwise, it's the old scheme. And you keep doing this repeatedly until the website is satisfied that you are the person you pretend to be, you claim to be. You know, you can implement this stuff using Product Computation. Your password is going to be a vector of bits of length n, where n is going to be fairly long. 1 or 2 would not be satisfactory, I think. Anybody would guess sooner or later what you're using. But if n is going to be long. Now, what is the challenge that the computer sends you? The challenge that the computer sends you is a random vector of bits of length n. You compute the dot product of your password and of the challenge, and you send out a bit. You repeat this many, many, many times. If every time you send back the right bit, then the computer will know with very high probability that you knew the password, the right password. Which is X. Now, one important point here is that when we compute the dot product, the plus is not OR, but it's exclusive OR. That's important if you want to do linear algebra with bits, because exclusive OR has the property that every bit has an inverse, uniquely defined. Whereas OR is not like that. There is no bit such that 1 or that bit is equal to 0. So 1 does not have an inverse with respect to OR. But with exclusive OR, it does. It's 1. The inverse is 1, because 1 exclusive OR 1 is 0. Okay, how safe is this protocol? Well, it depends. Suppose you are a nasty eavesdropper, and in the literature, the nasty eavesdroppers are always women for some reason, and they are called Eve. The guy is called Adam, typically. You got Adam and Eve, or Alice and Bob. Well, typically Eve is eavesdropper. So there's nothing gender-based about this. It's not that it's because it was Eve who took the apple and all that stuff. I mean, come on. We don't believe in that stuff anyway. Okay, so if you are Eve, how would you actually go about figuring out the password? All you see, you're an observer, all you see are the random vectors that the computer, the challenges, the vectors A1, A2, AN, and the bits that Bob or Adam sends back. You know what? You know the answer. And to convince you that you actually know the answer, let's figure out what Eve knows. There you are, Eve in green, because we love women. Sort of. It depends. Okay, Eve sees all the vectors that the computer sends to Adam. And actually, this is AM. The other thing that Eve sees, these are vectors. And Eve sees some bits, B1, B2, B3, that Adam sends back. And these vectors, well, are the dot products of A1 with X, and A2 with X, and so on. So what Eve wants to find out is the password, namely X. Okay, so what you have is A1 times sort of dot products with X should be the bit B1. You want an X such that A2 dot product with X should be the bit B2. AM dot product with X should be the bit BM. So your vector X here is some n-dimensional vector of unknowns. So what happens if I do the dot product, say A1, where A1 is A11, A1n. If I do the dot product of this vector with X. Now, what is it that I have? I have B1, but if I expand it using the definition of dot product, I have something like this, isn't it? So this should be an N. And this should be B1. But hey, I know A1, I know A2, I know AN. X1, X2, Xn are unknowns. I know the bit B1. Doesn't this look familiar? So I want to find the x's here. Isn't it like solving a system of linear equations? Your colleague is saying, what is the inverse of the A1? So this is a system of linear equations, but over bits, where plus is exclusive OR and times is AND. And you know, we can solve this system of linear equations just using elementary or operations. So actually, Eve can figure out your password by solving a system of linear equations. Not over real numbers, but over bits. Now, if you are the computer and the designer of the protocol, I think there is one thing that you want to ensure. Because you are the ones who send out, you are the guy who sends out the challenge vectors, A1, A2, AN. AM, sorry. Would it be a good idea to send out vectors so that this system of equations has only one solution? If this system has only one solution, how difficult would it be for Eve to guess the password? Would she need to guess the password? No, she would just need to solve the system of equations. Out comes one solution, that's the password. So you would want to ensure that the system of equations corresponding to the vector that you send out as challenge has infinitely many solutions. Or, well, it cannot be infinitely many because we are looking at bit vectors, but you want a lot of solutions, as close as possible to 2 to the n solutions, many solutions. So since we are looking at bit vectors, there cannot be infinitely many, but they could be 2 to the n, which is substantially better than 1. So actually, dot product can be used and is used in challenge response protocols for security. That's an example from real life. So next time you log in to a website, think about, okay, perhaps they're using dot product. They are not, probably, but perhaps they should. Even though it could be very boring to have to answer too many challenges before entering a website. I mean, what wouldn't you do for security? Okay, so I guess you're getting bored with all this real-life motivational stuff. You want some more formula. Oh, well, actually, let me give you another example. This is actually very close to here because have you ever heard about Identifier Forensics? It's a spin-off company from the School of Computer Science. Björn Thor Jonsson was responsible for some of the work that goes, this started as a master's thesis from some of our students who are now the CEOs, CTOs, super duper, Loopman, whatever, behind this company, Identifier Forensics. You can look them up. They are helping British police, for instance, figure out whether some videos are porn or not, amongst other things. Well, what is behind all this? Well, you know, there is, at a suitable level of abstraction, it's a linear algebra problem. Why? Because what are these videos? What are these pictures? They are nothing but vectors, huge dimensional vectors. So you want to know whether a vector is in a band list of vectors that represents porn photos. So how do you do that? Where you're looking for something which is called, well, we are solving an algorithmic problem, which is called nearest neighbor search. You got a set of points in some space, and you got a query point. For instance, you want to know whether this point is in the set. What you want to know is actually perhaps this point is not in the set, but is very close to a point in the set. For instance, this is a set of pictures. This S could be a set of pictures which are copyrighted. This Q is a picture that you want to find out whether it's been stolen from this copyrighted set of pictures or not. Well, if you're somebody who actually stole that picture, you don't reuse it unchanged. You Photoshop it a little bit. Well, where a little bit means a hell of a lot, typically. Otherwise, everybody will figure out that, wait, he stole my picture. So the output should be the closest point in my set of pictures to Q. And perhaps with some measure of how close that point is. Well, that's nothing but computing the distance between 2 points in a high-dimensional vector space. And since the distance between 2 points is a vector, and computing the dot product allows you to actually compute the length of that vector, there is dot product inside, perhaps carefully hidden, even in this thing. Even though to make this search particularly efficient, you need a lot of database technology. But the algorithmic problem is a problem about search in high-dimensional vector spaces, which has dot product somewhere in it. Okay, so these are some examples of applications of the stuff that you're seeing, and some of you are also learning in the linear algebra course in computer science applications that are being developed as we speak. Okay, well, orthogonality I've already told you. Two vectors are orthogonal, perpendicular when their dot product. In fact, you already figured that out. When their dot product gives 0 as an answer. So now we are at a position where I could start a new topic that has to do with vectors, but I don't want to rush through it. So we are going to do the new stuff, this next topic, which is the last, well, one of the two last topics that I want to cover in vector geometry. We are going to do this at the start of our next class, our next course session on Thursday. So any questions about what we covered today? Well, since we have time, I cannot resist you showing you another application of linear algebra before we close it off. So I don't have to do it next time round. Okay, secret sharing. Now I have a secret, which is the final exam. In fact, it's so much of a secret that I haven't written it down yet. So even I don't know it. But suppose that I have actually written it down. I represent it as a long vector of bits because I'm a computer scientist. And now I have these two TAs, Ertla and Ragnar, or Alice and Bob, if you wish, but Ertla and Ragnar is better. And since I want to go on vacation at exam time, I want Ertla and Ragnar to actually run the exam for me. But even though I trust them both, I don't trust any of them 100%. Because Ertla could be bribed. Ragnar could be bribed. But perhaps you don't have enough money to bribe them both. So what I want to do is to give each one of them part of the secret so that together they can reconstruct the final exam, but none of them can do it alone. So if you bribe Ragnar, for instance, you don't know anything about the exam. You need to bribe them both, and they're expensive. So you can't. Even if you pool or the 250 bank accounts that you have together. Okay, so how do I do it? I choose a random vector of bits. And then I take the vector for the exam, and I give that random vector to Ertla. And to Ragnar, I give the exam minus the random vector. So for them, it's actually very easy to figure out what the exam is. They just take their two vectors and they sum them together. But none of them has enough information to reconstruct the exam alone. And you know, this is all linear algebra over vectors of bits. You know the funny thing? RSA actually sells this stuff exactly in this way. We're back to the world of passwords. I think it's called RSA Secure Credential, whatever. In fact, probably I've written it here. RSA Distributed Credential Protection. So you know what RSA does? It's something that they sell. They tell you the following thing. Give me your password. I break it up into two sub-passwords, and I store the two sub-passwords in two different web servers. So that if an attacker breaks into one of the web servers, then he knows nothing about the password. He will need to break into the other one too and combine the two passwords in this way, in exactly the same way that I used for the Ertra and Ragnar example. So that's how you make money with simple vector operations. In this case, not even dot product, plus and minus. And since you want to do minus, you need to use XOR and not OR. Okay, and on this final example, you can feel free to leave the room. Well, you were also free beforehand, so it's...